Hey everybody, it's Ripley back again. Hope everybody's doing well today. We're going to talk pretty quickly about the finding the average value of functions using integrals. It's pretty cool too. It's super easy. And the proof of it is pretty neat as well. All right, so I've got a function on a closed interval from a to b, because clearly I've got to have it on a closed interval from a to b if I'm going to have an average value, right? Otherwise it's going to change infinitely. So we're on a closed interval from a to b. And I want you to think about this for just a sec. If I want to find the average age of a class, what do? I take all of the values of I take all the data values, in other words, all the ages, and I add them up and I divide them by n. So if you think about trying to find an average value of a function, there's nothing fancy to it. What I'm just going to do is I'm going to take a bunch of values of the function. So let's say f sub 2, f sub 3, and then dot, dot, dot. I don't know why I use commas. I need to add them up. Plus dot, 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 plus f sub n. And I'm going to divide by n. This is how you find an average. Let's write it over here. This is how you find an average, right? Now, you're like, well, wait a second, Ripley, aren't you cherry picking these values? Yeah, but we cherry picked before when we built rectangles. We know how to get rid of cherry picked values and add up an infinite number of infinitely small of these values, right? It's called this nutty thing called an integral. That looks like a negative. I gotta get rid of that, right? But just bear with me for a sec. So we got this n. How do we deal with this n? Well, if I recall, remember when we were learning about integrals, we knew that delta x was equal to b minus a over n. So n, do a little puff of algebra, is equal to b minus a over delta x, right? I mean, I can use this wherever I want. Hey, wait a sec, why don't we use it here? So watch what happens. I'm going to do f1 plus f2 plus f3 plus dot, 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 plus f sub n over b minus a over delta x. Well, with a little bit of algebra, what I can get is, and you're probably seeing where this is going, f sub 1, f2, f3 plus dot, 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 plus f sub n, put that sucker in parentheses, bring the delta x up on top, and divide by b minus a. Right? Now, think of this as like adding up areas of rectangles, even though we're not. What we're adding up is function values, right? But I want to I want to add up an infinite number of points rather than infinitely thin rectangles. So how do I do that? Well, I got this delta x sitting there. The thing is primed for me. If I want my average value, I simply take the integral from a to b of the sum of all of these guys, which is just f of x, right? dx, and I divide by b minus a. And that's it. That's how you find the average value of a function. It's really simple. You'll also see this written as 1 over b minus a, integral from a to b of f of x dx. Now, this can get a little bit confusing because we've got an average value of a function, and then we know about that you may confuse this a little bit, but I want to address this issue with average rate of change. The average rate of change of a function we know is equal to the slope of the secant line, which we know is equal to f of b minus f of a over b minus a. Remember from differential calculus. And you may say, oh, Ripley, wait, it's got a b minus a. This is going to get confusing. Well, it can get confusing, and you're going to have to sort of keep that straight. But watch. Rate of change. What is rate of change? It's the derivative. The instantaneous rate of change of any function is the derivative, right? So if I want the average of the rate of change, right? Now, bear with me for just a sec. The rate of change of a function would be f primed of x, true? So if I want the average rate of change, according to this formula, what I would be looking for is the average rate of change, the average value of the first derivative, correct? So this would equal the integral from a to b of f primed of x dx over b minus a, which we know the antiderivative of f primed of x is just f of x, and then I'm going to evaluate it at, well, hush my mouth, when I evaluate it at its endpoints, I get the same thing. I better get the same thing, right? If this is the average rate of change, this had better be the average rate of change as well. But don't confuse this. This is the average value. This is the average rate of change. I was just going off on a little side note. So average value right? And this is average rate of change. Okay, now there's something called, excuse me, the mean value theorem for integrals, but it's actually easier we can just build it out here. I'm going to change colors and I'll kind of cram it in this little space over here. Now, let's just look at this function. I mean, it looks kind of symmetric. I'm guessing that right about there is going to be my average value, right? If I do a little bit of algebra on this equation, do you agree on this guy right here? Do you agree that I can rewrite that as the average value times b minus a is equal to the integral from a to b of f of x dx? And you may be like, big deal, Ripley. All you did was like multiply through by b minus a. Woo woo! Well, no, it's more than that. Because what I just did is I showed that if I go over here to the function and put the average value on here, right? That's the vertical distance here. And then I build a rectangle that is b minus a wide and f av, the high, the area of that rectangle is always equal to the integral itself. In other words, an integral can always be expressed as the area of the rectangle built by taking the average value of the function and multiplying by the interval, right, from a to b. This is referred to as the mean value theorem for integrals. Now, this does not have, because it's not particularly earth-shattering, integrals, Ripley, for God's sakes, man, caffeine. This is the mean value theorem for integrals. This is not as earth-shattering as the mean value theorem for functions in and of themselves, right? Back in differential calculus. Remember, that wasn't all that hard either, right? It was pretty intuitive that we came up with that. But I think this is a really neat consequence of being able to find the average value of a function. Ladies and gentlemen, that's it. I'm done. So have a great day, and we'll see you in the next lesson.